want to thank you for inviting me for this presentation. It's the honor to be here. And my name is Egemen Aydin, and I am a senior student at Istanbul Technical University. And I would like to talk about our project in space Outgassing laboratory distant from Earth, or in a short name, ISOLDE. We inspired this name from a poem, The Twisting and ISOLDE. So, this is our management scheme of the project team. In this project, our main work for the terminal control system, but I have other part. Before start my presentation, I would like to thank all my professors and laboratories for their help in this project. So, this is my outline of this presentation. I will start with brief introduction, then I will go mission objectives, concept operations, and key performance parameters. Then I will talk about satellite design. In this section, I will talk about the subsystems of ISOLDE, but I will focus the scientific payload of our satellite. Then I will go implementation plan and projects. So, outgassing is a phenomenon, release of gases enclosed within materials. And this occurrence affects the electronics and optical devices. And these outgassing experiments are actually doing in the ground in vacuum tanks with clean rooms. But we can only achieve this lower vacuum, which is above than 10 to minus 6 Pascal. And also to achieve this vacuum is also very costly. However, spacecraft are operated in extreme high vacuum conditions. And this is the Rosetta's outgassing measurements in 6 years period. As you can see here in this graph, it's not single event, it's continuous process. That's why we have to investigate outgassing very carefully. And also I'd like to add that the outgassing in extreme high vacuum conditions are not investigated in detail. So our mission idea for ISOLDE to measure outgassing measurements on spacecraft in extreme high vacuum conditions. ISOLDE's period measure the outgassing rate and also contaminants from the sample material. We choose this sample material as a copper because copper is commonly used in spacecraft applications. And also we want to investigate the zeolite effect of outgassing characterization to another sample. Zeolite has a feature as the gas absorbing. And this is the molecular structure of zeolite. I'll talk about the main idea of ISOLDE, but I can summarize mission objectives of ISOLDE in 4 specifications. The first one, to perform outgassing measurements in payload with extreme high vacuum conditions. And secondly, to test contamination reliability while payload operates. And third one, to measure effect of zeolite. As I mentioned, it has the effect of gas absorber. And final mission objective is to provide data for the common spacecraft material with the prevention of return flux hazard. I can describe return flux hazard as an effect of outgassing to another outgassing measurements. And this is our concept operations flow chart. It starts with successful launch and orbit insertion. After orbit insertion, the ground station will send first uplink signal for the solar panel deployment. Then second signal will go for the pressure and temperature detection. After this confirmation, mission start signal will conduct. After pre-mission phase, the mission phase will start with extreme high vacuum condition confirmation. After that confirmation, experiment will start. And experiment will end in a week, and the data transfer will end in 2 weeks. And after the experiment is completed, the orbiting phase will start for the atmospheric reentry. And as you can see here in this image, we have uplink in S-band and downlink in X-band. In downlink, we have 3 types data. These are telemetry data, subsystem data, and middle data. And also, the sample material can be changed by the customer needs. To achieve these objectives, these key performance parameters needed to be achieved. And it starts with the attitude control system point the spacecraft to sun in order to keep payload at the same temperature. And successful heating for the subsystems because of sun-synchronous orbit selection. And our subsystems will be in shadow for doing our missions and achieving data storage from the sensors. and successful data transfer of 10 megabytes per second with the ground station. Actually, this data transfer rate, it's very challenging for us in that segment satellites. And the final one, the activating thrusters successfully for the deorbiting phase. This is the image of our payload. ISOLDE conduct these experiments in these two square-shaped laboratory units, named after Lab N and Lab C. Lab N has the copper sample and Lab C has zeolite sample. And also these laboratory units connected to each other via connector wall. And also these laboratories are connected to outer space. And these two residual gas analyzers are going to use for the count ionizing particle. And these three step motors are going to use for the wall mechanism of the payload. And of course, these chambers are going to vacuum in the ground to 10 to minus 6 pascals. And this is our subsystem applications. We designed the ISOLDE to take the base F payload. As you can see here, this payload segment here, our robust segment here, and this is the very cylinders. And we also, we filled the vacuums of the payload with water tanks. These water tanks are going to use for the thrusters for the orbiting phase. And these replacements are provide us more balanced spacecraft for the extended control system. This is our ISOLDE's budget in terms of mass and power. And we have approximately 180 watt consumption, power consumption. And we have 28 kilograms for total mass with margin. In extended determination system, it consists of 2 gyros, 1 3x magnetometer, 6 sun sensors, and 1 GPS. And also in extended control system consists of 4 reaction wheels and 3 magnetometer rods. In ISOLDE's electrical power system, to generate 180 watts, we use 48 gallium arsenide germanium solar cells. And command and data handling, we expect 29 gigabyte payload data for the 6 days of active mission. And we expect 74 megabyte engineering data. And our OBC has 216 gigabyte SD cards. And this is the image for our OBC. And ISOLDE has 5 operating modes. These are normal mode, step mode, emergency mode, communication window mode, and final one, the recovery mode. As I mentioned before, we use propulsion just for the orbiting phase. And as I mentioned, we use for that thrusters electrolysis of water. And for this deorbiting phase, approximately 4 kilogram water will be enough. And this is our telecommunication part, this is link budget of ISOLDE. We have uplink margin at 9 decibel and downlink margin at 2.2 decibel. And this downlink margin can be seen very low value, but to achieve high amount of data transfer rate, this was the optimal choice for our choice. And uplink frequencies in 7.2 MHz in S1, and we have downlink frequencies in 8.4 GHz in X1. We also use near network for the ground stations. And these are the subsystems temperature ranges. To stay between in these temperature ranges, we use passive control system. And to do so, we use Axon black plates. And with that application, we achieve the temperature range between 90 and 22 Celsius. And the structure and mechanism part, as I mentioned, we have 28 kilograms satellite. And for the base material, we use 6061 T6 aluminum motors. And as I mentioned, we use step motors in payload to operate wall mechanism. And we also use the chrome burn wire release mechanism for the solar panel deployment. And an orbit description, we choose sun synchronous polar orbit. because we want to generate more energy and it's easy to put in orbit. And to achieve extreme high vacuum condition, we choose 700 kilometers of altitude. Because of this altitude selection, we have to burn our satellite in atmosphere. This is our estimated project budget. And as you can see here, this manufacture and test will be held in Istanbul Technical University. And total cost, without launch, it's around $1.6 million. And total with launch, it's approximately $3.8 million. And this is our estimated project timeline. And launch and experiment phase will start in the first quarter of the 2018. And the orbiting phase will be in the second quarter of 2018. And also we have project risks. And of course any malfunction in this control determination system can be hazardous because of lack of power generation. And we can decrease these risks with using fault-tolerant critical control system. Actually, these systems is called in attitude determination control system. And of course, any possible leakage from water tank can be hazardous for the spacecraft. And we can eliminate these risks with doing ground tests. And the X-ray emissions are negatively affecting the quality of mass spectrometry experiments. And we can decrease these risks with using data correction and the radiation studies before the launch. And of course, any launch delay can increase the cost of the project, but in this case, we can consider to using another shuttle to decrease of the project. This is the cost of the project. This is my references. Thank you for listening.
So we have more than 10 minutes for questions.
So it looks like it's a good concept, and doing this research in space that makes a lot of sense. There are some opportunities also on Earth with high vacuum systems, but larger ones and expensive, and maybe that is a solution for universities and smaller entities. What I was stumbling about was the huge data amount you have collected within 6 working days, 29 gigabyte. Can you explain it a little bit? How it comes that you have this amount of data just for this simple looking experiment?
Yes, the experiment phase actually it's complete after 2 successful rounds. That's why we have this huge amount of data. This experiment started with another.
And the components which, I mean the 29 gigabyte is, you measure the pressure, you measure the outgassing
yes.
Constituents.
Yes, all.
And that specifically in different molecule sizes. And,
yes.
Okay.
And also I want to add something about our payload I forgot to mention. And our payload it's actually consists of 3 stages. At first stage we open up lab and the outer space to measure the effect of outgassing of copper. Then we will open up the conductor wall to measure outgassing rates of these gases. Then we will open up lab Z to understand effect of zeolite. And these processes are complete after 2 successful rounds. We're doing experiments twice to eliminate these radiation risks.
Okay.
Can you remind us, why did you go to 700 kilometers? What was your requirement?
Sorry, can you repeat this? Can you repeat this question?
Why did you go to 700 kilometers of altitude?
Because extreme high vacuum conditions starts with, it's around 680 kilograms of kilometers altitude. We choose this frontier, that's because.
Because the only concern is that you have a relatively large spacecraft.
Actually, it's not.
Yeah, but I mean, we're talking about CubeSat, you know, that's
Yeah.
relatively large. So you could save some money on the...
Actually, these costs are relatively low to consider another spacecraft.
Yeah. And then if you go to your payload, the one where you show the payload, what's the bottom half of it? Because you have all the, you know, all your sensors and the units and...
Actually, these residual devices are like is the whole of this residual devices.
Okay.
I have to ask the question about the ADCS system. In your cost breakdown, I think you said your ADCS system will cost about $13,000. Is that correct? 12. And it's a 3-axis stabilized system. You're going to use reaction wheels?
Yeah, we have 4 reaction phase price.
It may be that one wheel will cost you about $12,000.
Actually, it's not my profession then.
No, I'm just saying the cost breakdown seems to be a bit optimistic.
Yeah.
So this mission may cost you much more than what you had there on the list.
Yeah, maybe it's also the estimated cost.
The reason why the satellite is this specific size seems to be driven by the payload. The payload is quite big. Your ISOLDE payload is quite big.
Yeah, payload is quite big.
Yeah.
And
So there's no possibility of reducing the size of the payload?
No, because that's the smallest one. There's the Google devices. That's too big.
Is that the existing one?
Yeah, no, it exists.
Okay.
It's commercial part actually.
Okay, thank you very much. So I am still not very sure about the cost of performance of this, experiment, because it costs 3.8 million US dollars, right? Yeah, total is with launch 3.8 million
Yes.
US dollars, and I'm not sure. So this kind of this experiment has a value. Comparable with the 3.8 million.
Yes, we know that's what I'm saying. These tests are continuous in the ground at lower vacuum, and the spacecraft operates in extreme high vacuum. And these effects of outgassing in extreme high vacuum conditions are not investigated. And we want to do that.
Okay. So and this a level of the vacuum environment cannot be realized on the ground.
Yes.
Okay. They understand.
The question from the reviewers? No? So we have 6 minutes. So we can accept questions from the audience.
I'm hoping I didn't understand, but you mentioned you were sun pointing for constant thermal performance, but then you're in a sun-synchronous orbit which is going sunlight to eclipse. You would be better off in a dawn-dusk, constant illuminated orbit.
Actually, the bottom phase of the spacecraft are looking at always the Earth. That's why it's not very challenging part to do the thermal control because of sun synchronous oscillation.
Could you say that again?
Could you repeat your questions?
Well, I thought you were trying to maintain a constant thermal environment,
Yes.
and that's one of the reasons you're sun pointing. So there's two things. One is you won't be in constant thermal environment because you'll go into eclipse with your sun synchronous orbit, unless you use dawn-dusk sun synchronous, which will be always in sunlight.
No, we are not going to be in.
And related to that is you can remove your attitude control system just by spinning.
No, it's not. That's why we'll use sun sensors because the spacecraft are always looking at the sun. And it's around Earth. And the base, bottom of the spacecraft are looking at always at looking Earth. I could explain it.
Any other questions?
Do you need a XHV inside the satellite?
Sorry?
Do you need a extremely high vacuum inside the satellite? Do you need a extremely high vacuum inside your satellite?
No, we don't need, because we open up these valves to get extreme high vacuum.
So
The laboratory units are connected to outer space.
it is connected outside space. And however, there will be outgassing from the satellite body itself.
Sorry?
There will be outgassing from the satellite bodies. And did you estimate how quickly you can achieve the vacuum?
Actually, I don't know.
Yes, I think there are lots of the studies who worked on the outgassing rate in space, and result shows you don't get the high vacuum so quickly. There are lots of the gases coming out even after months after.
One last question. Your satellite you're saying is in a dawn dusk orbit, flying constantly in sunlight, sun-synchronous orbit, but you need black paint to do the thermal
Yes.
stability. It seems a bit unlikely to me if the satellite is constantly seeing sun that you will have a black paint with a very high absorptivity. So I would say you don't need to cool down the satellite, you need a white paint. Where does that black paint come from?
The sun sees that's only to the solar panels. The other parts all in shadow. That's why we use black paint
So
to...
the solar panels is solar cells
Yes,
that absorb the solar energy.
yes,
Where's the paint?
yes. That's the only one to consume heat. The other parts don't see any sun. That's why to keep heat inside we use Hudson black paint.
Black paint where? On the other sides that doesn't see the sun.
It's not about the absorbance, it's about all emissivity.
Okay, so you want high emissivity and low absorptance.
Yes.
So maybe black is not the right thing to use.
No, we already did the calculations. It's this range. It's between two range, this range.
Yeah, okay.
Any other questions? No? Okay, thank you.